Start this video with the next item on the what you need to know list, which is electrophoresis. And there are many ways you can do electrophoresis. It's basically separating out particles based on either their size or their charge. The type I'm going to show you right now separates them based on their charge. So let's say I had this electrophoresis apparatus. I had a positive electrode over here, a negative electrode over here. And let's say I have a pH 7 buffer, okay? So that means all my amino acids are at a pH of 7. And let's say I put a bunch of amino acids here, okay? Let's say this one is alanine, this one is lysine, this one maybe is tyrosine, and this one is, let's say, aspartic acid. Okay, so these are 4 amino acids, and I want to separate them out using this apparatus here. Okay, now think about the structure and what category these are in. Alanine is in the nonpolar side chain. Lysine is basic polar. Tyrosine is polar neutral. And aspartic is polar acidic. All right, if you look at the side chains, aspartic acid at a pH of 7 is going to be negative. Remember, the carboxylate ion on aspartic acid is going to look just like the carboxylic acid, the C terminal part of aspartic acid. So they both have a negative charge. The amine group has a positive charge. So net aspartic acid is -1. The -1 aspartic acid is going to be attracted to the positive electrode. So aspartic acid is going to move in this direction. Tyrosine is polar neutral. It has a plus charge on the amine side, a negative charge on the carboxylate ion charge. So it doesn't have an overall charge at a pH of 7, so it's going to just stay put right here. Lysine is basic, it's polar basic. Its side chain has a positive charge, and so it's got a total net lysine at a pH of 7 of +1. So it's going to be attracted to the negative electrode, so it goes over here. And alanine is nonpolar. It has a net charge of 0 at pH of 7, so it's going to stay put. So you're able to separate these two out from these two. So these two are over here, so you'd have to use something else to separate these two guys. But this is just the basics that we're just going to cover in this class, and I just wanted to give you a heads up on that. All right. The next topic is create some peptide bonds. So let's create some peptides. A peptide bond is an amide functional group. Do you guys remember amides from the amine and amide chapter? An amide is a carbonyl N. So if I drew out, let's say, just going to draw this amino acid here. I'm just going to draw it out in this format, not as a zwitterion. I'm just doing it like this. And then I'm going to have another one. Let's say I've got this one. Let's see if you can recognize these guys. Oops. This is an alanine. And this is a glycine. So this is a glycine, and I want to bond it to an alanine. All right. When you create a peptide bond, you remove a molecule of water. So you're removing an HOH. So you should be able to see that you're going to be linking these two guys. So you can see that there's an HOH. See this H and this OH. We're going to take that molecule of water away. There we go. And create a peptide bond. So this over here peptide bond, carbonyl, and it is an amide functional group or a peptide bond. What we just did was we created a dipeptide. A dipeptide is made up of 2 amino acids and they are bonded together by 1 peptide bond. If I did a tripeptide, it would be 3 amino acids and they're bonded together by 2 peptide bonds. If I did a pentapeptide, that's 5 amino acids and they're bonded together with 4 peptide bonds. All right, so let me show you a peptide at different pHs. Now let's put some charges in there, make it a bit more interesting. So I'm going to draw this peptide here. Let me get this one right here. I'm going to draw this peptide. I'm going to draw glycine, serine, lysine, aspartic, and let's do one more. Which one should we do? Tyrosine. Okay? So if I was going to put the single letter abbreviation, this would be G, S, K, D, Y. All right? Now, this side over here is called the N-terminal. This side over here is the C-terminal. You'll see why that is the case as I'm drawing them out. The N-terminal, now I'm going to draw them with charges. So we're just going to imagine that we're at a pH of 7 here. So at a pH of 7, remember all the amine groups are protonated. They're ammonium ions. All right, now we're going to do serine. So can you see the carbonyl, the carboxylic acid group is now hooked up as an amide bond between this amino acid and this second amino acid. So it's always going to be a nitrogen, alpha carbon, carbonyl. Nitrogen, alpha carbon, carbonyl. Nitrogen, alpha carbon, carbonyl. We're just going to keep on going. Okay. There are no charges on the peptide bond at all. Okay. This is going to be my lysine. The side chain of lysine is going to look just like this ammonium ion because it's polar basic, just like we said. Aspartic is going to have a charge also because it's polar acidic. So this is aspartic. It's got a charge. And then the last one's going to be tyrosine. Remember my favorite amino acid. And put this over here. Again, all these side chains could be flipped up. They could be put in lots of different ways, but I'm just going to choose to do it this way. And there's the tyrosine. All right. So I want you to take a look at this carefully. Look and see what I'm doing here. I've got 1, 2, 3, 4, 5 amino acids. The N-terminal amino acid is glycine. Why is it called N-terminal? Because this amine group is not hooked up in a peptide bond. The C-terminal amino acid is tyrosine because this carboxylate ion here is not hooked up in a peptide bond. Okay. You notice that there are no charges on any of the peptide bonds. This pentapeptide has 4 peptide bonds. Here's 1, 2, 3, 4 peptide bonds. This overall charge of this peptide here, this pentapeptide, you see a plus here, a minus here, and a minus here. So the 2 minuses cancel out the 2 pluses. So here it has a net charge of 0 at a pH of 7. Now we're going to take the same pentapeptide and we're going to dump it into an acidic environment. So now let's say we're at a pH of 1, super acidic. Okay, remember what happens in a super acidic environment. Anything that can get protonated gets protonated. So all the carboxylate ions pick up a proton. Leave these guys alone, but this is a carboxylate ion, this is a carboxylate ion, so it's going to pick up a proton because we have an abundance of protons now. So now this is going to pick up a proton, the H plus cancels out the minus. So now we're not at a pH of 7 anymore. We're at a pH of 1, super acidic. What would the net charge of the pentapeptide be? You can see that there are 2 pluses, there are no minuses. This pentapeptide has a net charge of +2. Okay. Now let's say you take this and you put it in a super basic environment. Very, very, very basic. Anything that can donate a proton is going to donate a proton in this super basic environment. So we're at a pH of 12 or 13. What's going to happen? Well, the ammonium ions lose 1 proton. The carboxylic acids, of course, lose a proton. They lose them pretty early. So these guys lose a proton. And this is something I haven't told you about tyrosine, but tyrosine is the only polar neutral amino acid whose side chain gets affected by pH. And it only gets affected by pH at a really, really high pH. So this phenol group of tyrosine actually loses this when the pH is super high. So our tyrosine is going to lose a proton, the phenol group. The serine, don't touch it. None of the other polar neutrals lose any. See, my Siri always thinks I'm talking about her when I talk about serine. None of the other polar neutrals lose any protons, just tyrosine at a very high pH. So if you take a look at this, we have a negative, negative, negative. At a pH of 13, this pentapeptide has a net charge of -3. Okay, good. We will start talking about different types of levels of protein structure in our next video.